All right. A few lessons ago, I talked about the scientific method. Now let's get into this idea of the scientific method in detail. Again, remember that I talked about how, you know it and all that, but it's always good to review it and to get an idea of how we use this in a forensic sense. So let's do that, shall we? We talk a lot about what science is and what science does and what info we get from science, but we need to understand what science is and how it works before we can use it to find answers about the world. It's that idea of understanding the basics before you can apply it. So, at its very basic idea, science is the process of discovering how the world works, which is one of the reasons I love it. It's the process of discovering how the world works. Notice that I said it's a process. It's not a collection of facts. It's not a collection of theories. It's not a list of publications. It's an ongoing process. It is constantly in motion. It's a concerted effort to uncover concepts and illuminate how the world around us works. Now, you're part of science by going to a university. You are actually trying to figure out what people have already known so we can get you to the very edge and start learning new things around the world and telling the rest of the world about it. This is why I adore science. I'm just going to keep saying that. In science, we use ideas and information in order to uncover those concepts about the world. The first thing we use are facts. So you use this word fact quite a bit. Facts, when we talk about science, these are things that are observable and indisputable. So facts are just things that are. So you could do something like, I am sitting in this chair. That is a fact. You could come and see me sit in this chair. You can observe it. I am sitting in the chair. The end. So that is what a fact is. Observable and indisputable things. Now, data, on the other hand, is any piece of information. So data are pieces of information that we usually gain through experimentation. So we got our facts, the things that are indisputable, observable things, and data, any piece of information. Now, just a quick aside, the word data is plural. Whenever you see that, it's plural. And so this is a thing that goes back and forth a lot in not the literature, because you'll get reamed by peer reviewers if you do this wrong, but in pop culture. Datum is the singular. Data, we have a lot of pieces of data. Okay, so these data are is the way that you say it. So just on the side there. Although you'll notice that even I will use data as singular every once in a while, so it's not that big a deal. Anyhow, so this is usually gained through experimentation. So just to give you an example of what I mean, let's say I want to know how quickly a maggot grows based on temperature. So I could take this maggot, I can observe these maggots. We know that they grow based on temperature. Remember that scientific method thing? Okay, we know that they grow faster when it's warmer, slower when it's colder, but I need these actual pieces of data to figure out exactly how quickly they grow. So I could take these maggots and I can put them at different temperatures. I can put a group of maggots at 15 degrees Celsius, another group at 20 degrees Celsius, another group at 25. And then I can watch them grow and I can check them every hour. And I can see when they go from the first to the second to the third instar. I can see how big they get over time. Each bit of observation, each little piece of information that I write down, that's my data. I've experimented on it, I have changed some variables, and now I can compare and contrast the data. Now, once we've gathered facts and data, once we've looked at all these bits of information, this is when we start creating a tentative explanation for the observation, for the phenomenon, for the scientific problem that we're looking at. So this we call a hypothesis. So hypothesis This is a tentative explanation. Some people call it an educated guess, and that's a very apt idea. And although other scientists don't really like it when you call it a guess at all, they say, no, there's actual information in there. But it's an educated guess. You take this information, you're trying to come up with an explanation for what you see, for this scientific problem, but it has to be tested. So simply put, it's an explanation for what we see that can be tested by further investigation, by further experiments. So that's the key. It explains facts and it explains data. It explains those observations that we made. It explains what we saw, that data that we collected during the experiment, and all of it fits. If the hypothesis does not fit, you change the hypothesis. You don't change your data to fit the hypothesis. No. A hypothesis is one of those things that should be fluid. It should be constantly changing based on new information. So you design experiments to test if that hypothesis holds up. These hypotheses should be tested over and over and over again by changing things a little bit, by adding in new information, by taking new observations. And each test, each experiment brings new information to the table, which then allows the hypotheses to be refined, to be strengthened. Unfortunately, you will run into things in science where people get very protective of their hypotheses. They come up with this hypothesis, this idea that explains some information. They run some experiments, though that data that they collect seems to support their hypothesis, and it keeps going. Then somebody else comes along, and that someone else, it comes up with a different experiment and a different set of circumstances, and suddenly that hypothesis is called into question. In a perfect world, everybody would be like, ooh, interesting. Let's refine this hypothesis then as a group. But that's not what happens. When you pour your whole life into this hypothesis, you become really protective of it. And you consider it your legacy, right? And then if somebody comes along and disproves it in some way, they're not... In a perfect world, they're not saying, hey, you are just crappy, I almost cursed there, sorry, crappy investigator. What they're saying is this hypothesis does not fit the new information. But some people take it very personally, and we end up getting people who just dig their heels in, and they just say, nuh-uh, you're wrong. And instead of taking this new information, they will go off on the scientist or the science or whatever else. And you end up with some pretty epic fights in the literature, especially. It's actually pretty fun to watch. Anyhow, so this hypothesis should be fluid. You should be able to refine it. It should be strengthened over time. Once we have a long time of looking at these hypotheses, of refining these hypotheses, of using numerous hypotheses to explain a particular bit of information, and over many, many years, many experiments, and many different scientists, if we have been unable to disprove any of these hypotheses, remember, you can't prove a hypothesis. We can support a hypothesis and we can disprove it. Cannot totally prove it. But if we're unable to disprove it, then that's a pretty good indication that this just might be the way things are. That's when these explanations become an overarching theory for how something works. Now, this is a bit of a pet peeve of mine. I see this a lot in literature. I see this a lot in pop culture, in just sort of normal day-to-day talk where people talk about a theory as something that is iffy. Well, it's just a theory. No. In science, a theory is an explanation for an observation or phenomenon that is based on a large amount of evidence. When I talk about a large amount of evidence, I'm not just saying somebody did a really big experiment. I'm saying multiple people over multiple generations did many experiments. And there is so much overwhelming data for this that we have not been able to dispute it. We just haven't. We have refined these hypotheses so much that it just is supported so well that it is really synonymous with a scientific law. So when we talk about this idea of a theory, it isn't as wishy-washy as it may sound. So you'll hear people, especially on the news, they'll say things like, well, it's just a theory. Okay, well, gravity is just a theory. We cannot in any way say that the theory of gravity is completely indisputable, but there's so much evidence for it that, it's pretty much a scientific law, right? So it's just simply a whole bunch of hypotheses about gravity, about why things fall down when we drop them, that has been tested so many times that it has become nearly a fact. But when we talk about these hypotheses and these theories, we cannot prove anything. We've been burned before. And that's really what this is all about. We're basically a scientist covering our butts here. We're saying, well, this is a theory, the theory of gravity, the theory of relativity, the theory of these things. So if and when we get new information, we can add it into that theory. And it is a lot easier to change a theory than to go back and be like, well, we called it a fact, and now it's not. That's just embarrassing. So a theory is synonymous with a scientific law. So when I talk about a scientific law, the law is a statement which describes patterns in nature with no known exceptions. So this law, this is just something that it's a system of ideas, really, intended to explain something, intended to explain patterns, it's intended to explain biology or chemistry or whatever, especially one that is based on a general principle, independent of the thing to be explained. Okay, so it is something that can predict what's going to happen under a variety of circumstances. It can predict how things are going to react. It can do these predictions. It can explain what you see, what happens, because it is this scientific law. So in order to get these overarching theories or overarching laws, this is where that scientific method comes into play. So our scientific method. Scientific method is a body of techniques for investigating phenomena, for acquiring new knowledge, for correcting and integrating previous knowledge, for taking all this information that we have. And if you look at this body of evidence, if you look at the way we see things, it's sort of piecemeal, right? You get scientists looking in one area and really going into depth in one area, and other scientists looking in another area. And maybe those two things are related, but it takes generations of scientists to figure that out. So then you can take it all and integrate it together. But in order to be called scientific, this method of inquiry must be based on empirical and measurable evidence. So when I say the word empirical, this means information acquired by means of observation or experimentation. So in this case, we looked at something, we measured it, we experimented on it by changing all these different variables, we saw how it reacted. So this empirical evidence, this measurable evidence has to be accurate and it has to be precise for it to actually be scientific. So you want to make sure that you have actually good data, proper data from which to draw your conclusions. This is where the This is where a lot of conflict can come in between those people who are trained as scientists and those people who are not. The idea of empirical evidence is very difficult to grasp if you haven't been trained through your science courses. You haven't learned to look at observations and data and hypotheses in a different light than theories and laws. So a lot of people will take something as fact based on anecdotal evidence, not empirical evidence, not this observation and experimentation evidence, but on, well, I heard a bunch of stories. So I like to say the plural of anecdote is not data. Just because you have a bunch of people telling you stories that all seem to match up doesn't mean that is good scientific data, because it is not done via the scientific method. Now, a big problem that the scientific community has also run into over the years, and a major reason we now use the scientific method, is bias. Remember we talked about forensic science and bias and all that jazz? Yeah. A famous scientist once said, smart people can come up with very good explanations for mistaken points of view. This encapsulates bias beautifully. It is very easy to think your way into an answer without having any evidence to back it up. Just look at Facebook or look at any social media and people with really strong opinions. You can talk yourself into believing something really easily. It's what we do as humans. That's our bias showing. So the way that we do this is heavily influenced by personal and cultural beliefs. Scientific method, this is a way to minimize the influence of our background, minimize the influence of our cultural beliefs, our personal beliefs, our experiences, our prejudices, basically a way to minimize our bias when we run experiments. Because we're human, we're going to have bias. It's going to happen. And a lot of times, since we're living in it, we can't notice it. We don't know when we are biased. So we've worked on perfecting the scientific method instead. We've worked on perfecting the set of rules that help us take that idea that we are going to have bias. We are human. It's fine. But we're trying to remove that bias as best we can from answering our questions. So the idea of the scientific method is based on the ability to first reason out an idea, to use that strength, which really is a strength, to take all these different observations and stories and things and come up with an idea of why it all works, but then experiment to see if things actually work the way you thought. Now, if your original idea is contradicted by an observation, then it's proven false. You have actual data showing that your hypothesis, that your thought was not correct. But that gives you this new opportunity to use this new information to try to explain things differently. Now you have a new part to the story. So even though you thought you were correct given all your information, now you have new information coming in. You need to change your hypothesis. So this is called falsification. This is a key part of science. Every question you ask, every experiment you run must be phrased in such a way that it is falsifiable. So given the correct equipment, given the correct techniques, given the correct methods, you can falsify this. What it does is it eliminates something called confirmation bias. Confirmation bias is the tendency of people to favor information that confirms their beliefs or their hypotheses. Again, just look to social media. You will see confirmation bias all over the freaking place, right? People will pick and choose their information based on what they already think or know to be true. And then they will present that as fact. It's easy to do, it's comfortable to do, and even the greatest scientists in the world will find themselves doing that because it is really hard to see other points of view. When you get into the scientific realm, though, you have to be ready to take your hypotheses, to take your ideas, and modify them based on new information. So the scientific method can be thought of as an attempt to disprove your ideas. You have an idea, you're going to do your damnedest to disprove it, using all these proper techniques, using all these different ways. The more times you fail to disprove an idea using empirical and measurable evidence, the more likely that idea is to be true, the more support you have for that idea. All right, so that's enough about that portion of the scientific method. Let's get on with it in the next lesson. Let me know if you have any questions.